So today we're going to start talking about quantum effect calculations. And the first thing we're going to talk about is black body radiation. So a black body is a body that absorbs all the radiation that's falling on it, and when it's hot, it also emits radiation, and the spectrum of wavelengths and frequencies that it emits depends on its temperature. So the plot that you see there is for 3 different temperatures, 3000, 4000, 6000 Kelvin, and you can see that the wavelength at which they have their peak frequency varies depending on the temperature. And we talk about how hot something is often by what color we see it. So we say something's red hot or white hot. So something that's white hot, you see it emits in all the visible ranges at a very high rate, and so then that makes it look like it's white. So Wien's law says that the position of the peak of the wavelength is given by a constant 2.90 times 10 to the minus 3 meter kelvins divided by the temperature. And to get this right, you must put the temperature in Kelvin. So let's quickly do a calculation. The star Rigel has a peak in its emitted radiation at a frequency of 2.07 times 10 to the 15 hertz. What is its temperature? So we know that the wavelength is 2.9 times 10 to the minus 3 divided by the temperature in Kelvin. So we want to find the temperature. If I rearrange that, the temperature is equal to 2.9 times 10 to the minus 3 divided by the peak wavelength. Now what do they give us? They give us the peak frequency. So we're going to have to turn frequency into wavelength. So remember, C is equal to F times lambda. So lambda peak is going to be the peak speed of light divided by the peak frequency. So it's going to be 3 times 10 to the 8 divided by 2.07 times 10 to the 15. And so I get a peak wavelength of 1.449 times 10 to the minus 7 meters. And then that is what I'm going to put into that equation there. So the temperature is 2.90 times 10 to the minus 3 divided by 1.449 times 10 to the minus 7. And I get a very high temperature, 20,000, and the units are Kelvin. So if you're given a frequency or wavelength, you can find the temperature of the star, which is how astronomers figure out what temperature a star is at. Or if you're given the temperature, you can figure out what the peak wavelength or frequency will be using that equation. All right, so Einstein suggested that light must be emitted in small energy packets that he called photons. So a photon is a particle of light, has 0 mass, and its energy is equal to Planck's constant h times the frequency at which the light is going. And de Broglie said that, well, if light can be a wave and also a particle, then maybe anything that's a particle that's moving, so it has a momentum, can also be a wave, and the wavelength of that wave will be Planck's constant divided by the momentum. And for most objects in everyday life, this wavelength is too small for us to observe, but we can diffract very small particles like electrons that are moving at high speeds. So let's do a couple of calculations with those two equations. So first of all, let's calculate the energy of a photon that has a frequency of 5.25 times 10 to the 14 hertz. And they want us to put it in both joules and electron volts. So our equation is E is equal to H times F. So H is 6.626 times 10 to the minus 34 joule seconds. And you'll see there it's given in 2 sets of units, both EV seconds and joule seconds. And you can use either depending on whether you want the energy in joules or electron volts. So multiply times the frequency, and I will get the energy. The units of hertz and the units of seconds will cancel out, and so I will get an energy of 3.48 times 10 to the minus 19 joules. If I want to put that in electron volts, Remember, 1 electron volt is 1.6 times 10 to the minus 19 joules. So the energy is also, if I do the conversion, so I write down my energy in joules, do the conversion. I want to get rid of the joules and go to EV. So I write the fraction that way up. I get 2.17 electron volts. I could also have just recalculated the energy using the value of Planck's constant in EV seconds as well. Okay, calculation using de Broglie's equation. So what's the wavelength of an electron that has a speed of 2.651 times 10 to the 8 meters per second, so pretty close to the speed of light, and we know the mass of an electron. So we would just put the numbers in there. So the wavelength is Planck's constant, 6.626 times 10 to the minus 34, divided by the mass, 9.11 times 10 to the minus 31, times the speed, 2.651 times 10 to the 8 meters per second. And I get a very small wavelength, 2.74 times 10 to the minus 12 meters. So that's maybe much smaller than the size of an atom, nearing the size maybe of a nucleus of an atom. But if I make my speed a bit smaller, in the denominator, I can get the wavelength up to be similar to the spacing between atoms in a material, and then I can make that diffract. Okay, so the real reason that Einstein came up with the fact that light is a photon was he was looking at the photoelectric effect. So remember, for the photoelectric effect, when you shine light on a surface of a metal, what they found was that electrons could be emitted, but the energy of the electrons that were emitted depended on the frequency linearly, and below a certain frequency of light, there was no electrons emitted at all. So if light is a photon, a particle of light, then what we can imagine happening is that as we have each photon, little particle of light coming in and hitting the surface, it can knock out one electron. And so if we have higher intensity light, what that means is that we have more photons hitting the surface, and so we'll have more electrons emitted. The kinetic energy at which those electrons come off is going to depend on the energy of the light that's coming in, which is HF, minus how much energy it takes to pull the electron out of the surface. And we call that the binding energy, so BE, or sometimes it's called the work function, W0. So the kinetic energy of the electron is the energy of the incident photon minus the energy required to pull the electron from the surface. And so if the energy of the light is less than the energy that you need to pull the electron out of the surface, you're not going to be able to pull out any electrons from the surface, and so there won't be any light emitted. So let's do some calculations. So the work function for gold is 4.58 electron volts. So that's how much energy it's going to take to pull it out of the surface. We want to find out what's the minimum frequency of light for which you can pull electrons from the surface. So the minimum frequency would be where we have zero kinetic energy. And so then the energy of the light coming in, H times F0, is just going to be equal to the work function. So we've got our work function energy in electron volts. So let's do the calculation. Let me see if I can erase that. Let's do the calculation with our Planck's constant in the units of electron volt seconds, and then that will give us a frequency in hertz. So F0 is 4.58 electron volts divided by 4.136 times 10 to the minus 15 EV seconds. And so then I get a frequency of 1.106 times 10 to the 16 hertz. Okay. Alternatively, you could take that energy in electron volts, turn it into joules, and use the value for Planck's constant in joule seconds. You'll be given both of these on the equation sheet on a test, so you'll be able to use whichever you want. Okay, so next one, what if we shine on light that has a frequency of 2 times 10 to the 15 hertz? What's the kinetic energy of the light that will be emitted? Okay, so I've got kinetic energy is HF minus the work function. Okay, so my work function, I have an electron volt, so let's keep Planck's constant in electron volts. 4.136 times 10 to the minus 15 eV seconds times the frequency, 2.0 times 10 to the 15 hertz minus 4.58 electron volts. And when I plug that in, I get 8.283 electron volts is my kinetic energy. If I want to put that kinetic energy into joules, I can do a conversion in joules. We'll go the opposite way to what we did for the other one, so let me just show you. So I want to get rid of the EV and go to joules. So I write my fraction up the opposite way to what I did for the previous example. So I get 1.33 times 10 to the minus 18 joules for the kinetic energy of the material. Okay, so while I was looking at that, I noticed that I made a mistake up here in writing my number. This is 1.106 times 10 to the 15 hertz is my minimum frequency. Okay, so obviously, if it were 1 times 10 to the 16 hertz, and I shone on 2 times 10 to the 15 hertz, that would be too low, and so we wouldn't get any electrons emitted. So my answer there should have been 1.106 times 10 to the 15, not 10 to the 16 hertz. Okay, so what do I want you to do today? I want you to do just a photoelectric effect calculation. So here we've got a material that has a work function of 2.3 electron volts. I want you to just repeat what I did there. What's the minimum frequency of light required to pull electrons from the surface? What's the maximum kinetic energy of the electrons emitted? So that's what I just did. And then based on the kinetic energy, you can find the de Broglie wavelength using lambda equals h over p. And you can use the conversion. Remember, P equals mv, and kinetic energy is 1/2 mv squared. So that means that I can find the momentum compared to the kinetic energy. P squared is 2 times the mass times the kinetic energy. So it's just a shortcut there, or you can rearrange it, find v, and calculate p. So the mass of an electron is given at the bottom. And then there's a trick question. What would happen if you shone light on that had a frequency of 3.5 times 10 to the 14 hertz? What would be the kinetic energy of the electrons that are emitted?